Welcome back to Troubleshooting Python Machine Learning. Today we're starting a new section on defeating regression and classification difficulties in Scikit-learn. In this section, we're going to take a look at 4 different problems that you encounter when you're doing standard tasks like regression and classification in Python using Scikit-learn. The first issue that we're going to look at is finding the most important features after you've trained your classifier. The second issue is classifying items into multiple categories. The third issue is retrieving the best estimators after you've done a grid search on any of your models. And lastly, we're going to look at how we can get a richer output from doing linear regression on any pandas data frame. Let's dive into it. In this video, the topic is finding the most important feature in your classifier. In this video, we're going to take a look at 3 different things. Number 1, what is feature importance in linear classifiers? Number 2, how can we use feature weights as a proxy to the classification decision? And number 3, how can we use standard deviation to normalize model coefficients? And you'll see later why this is important. But then overall, the topic that we've picked today for the video is important because often you need to explain as a data scientist to non-data people why your model is saying what it is saying, right? Like there is a particular field in machine learning research around interpretable models. And it also appears a lot in the industry where, for example, if you have a credit scoring algorithm or fraud detection algorithm, what you want to do is for cases or accounts where it needs manual review, you want to feed the triggers of this high score to the manual review team so that they understand more why this case is coming to their attention. And that's why understanding which features are important that contributed to the decision at hand is very important. Let's dive into Jupyter Notebook and have a look at how we can do this. So we're back here in our Jupyter Notebook, and needless to say, you can find all of this in the attached code files that comes with these series of videos. The first thing we want to do to explore this problem is to import our normal data science packages like NumPy and Scikit-learn. Today, especially, we're going to take a look at using logistic regression to understand what important features have contributed to the classification decision. Let's also import that from Scikit-learn. Great, so imported these packages. The next step that we want to do is to create some dummy data. Dummy data is a very useful tool for you to understand whether your models or your data science pipeline is working correctly because you control what the dummy data looks like. In our case, what we want to do is create a linear combination that determines the class of a binary classification problem. In particular, one of the features is going to be more important than the other 2 features, and we want to see whether our important features code can actually pick out which feature is important. So we have feature 1 simply being a series of random numbers. And then we have feature 2, which is also a series of random numbers. The difference here is feature 2 is 4 times more important than feature 1. And we add in feature 3, which is actually half as important as feature 1. And the reason why we can almost too straightforwardly say that the coefficients, the numerical values of the coefficients of these features determine how important they are is because we're simply going to assign the 2 classes in this binary classification problem between 0 and 1, and whether it's 0 or 1 is determined by whether the total linear sum is larger than 0, right? So you can imagine if we multiply feature 2 by 4, that means it contributes 4 times more to whether any random number would make the whole sum larger than 0. So class labels to, let's add an intercept, and then we have feature 1, 2, and then let's add some noise to this as well. And whether this is larger or equal to 0. Let's see whether these calculations make sense. Looks fine. And we can assemble this into a design matrix using the column stack function, which stacks 3 columns, feature 1, feature 2, feature 3, into a matrix, right? As with all of our scikit-learn models, what we need to do first is to initialize the model, and then we then need to fit the model on the data. Again, scikit-learn helpfully tells you what logistic regression model it has initialized, and so that you can reference it later if you want to put this in production or something. The very standard way for us to understand how the model has fit the data is to look at the coefficients. So let's take a look at the coefficients. As you can see, all of these coefficients are roughly of the same magnitude, and it really isn't a good way for us to discern which features are more important and which features are less important. For example, if you look here, if we simply say, is the largest number in this array the determinant of what's an important feature, then we'll pick the first feature as the most important feature, which, as we know, because we've constructed the dataset, this is wrong. The issue here of why you can't just take the model coefficients and determine the feature importances is because the scatterness and the scale of different features are different, right? Because here we're spreading feature 1's values are spread over a ball between 1 and 0, but then feature 2, because it has a multiplier of 4, has a spread 4 times that. So it's very hard for you to understand what the coefficients mean if the scale and the location of your features are not the same. So one quick and easy fix to this is we can divide the model coefficients by the standard deviation. So the way we do this is we simply calculate the standard deviation of the design matrix, in which case it gives us the standard deviation of feature 1, feature 2, and feature 3. What we then need to do is multiply that with our model coefficients to scale our model coefficients according to the standard deviation of their underlying data. As you can see here now, we now have a very nice situation where we can simply pick the max number in this array to indicate what features are important and what features aren't. And you can't do that before. We want to note that if we standardize the data before we feed it into the model, much like the requirements of a lot of models in machine learning, we can achieve the same effect with just model.coefficients, because now the scale and location of each of your feature columns will be the same. So what have we just learned? We've just learned that feature importance in linear classifiers is a very useful tool when you deploy linear classifiers in the real world and you need to communicate why the classifier made a decision the way it did to stakeholders or teammates who aren't in the data science area. We then looked at feature weights as a proxy to the classification decision, but we figured out that actually the feature weights aren't very informative unless your data is standardized in terms of scale and location. We then learned whether we can divide the model coefficients with the standard deviation to produce importance either before we fit the model or we can multiply the model coefficients with the standard deviation after fitting the model to produce a good importance score. And that's how we can do this.